I'm now happy to introduce Daniel Egger, who is a staff research scientist at IBM Quantum and more specifically at IBM Research Europe. Daniel, on your research, you focus on the control of quantum computers, how to integrate them in modern software stacks, as well as on the practical applications of quantum algorithms in finance, optimization, and natural sciences. In your talk, I understand that you will discuss a framework that integrates classical and quantum computers using an open source middleware built on Qiskit, I think it's called. Daniel, welcome on stage and all the best.
Thank you. All right. Hello, everybody. As mentioned, my name is Daniel. I'm based in IBM Research in Zurich. And today I'd like to talk about integrating high-performance high-performance computing with quantum computing. I think here we have the beginning of the end of the presentation first, so I'll just move all the way back to the start. So bear with me. All right, there we go. Right. So, how do I go forward? Oh, the green one. No, the big one. Oh, that one. All right. Sorry about that. Okay. So, what I will do, I'll give a short introduction, the motivation for quantum for us, for IBM, and present our roadmap, which you've probably already seen. I'm sure that Heike has discussed it also yesterday. And then I'll go over some of the middleware for quantum. I'll discuss the quantum serverless and the circuit knitting toolboxes that we have. So the mission that we have at IBM Quantum is to bring useful quantum computing to the world. And this is essentially what drives us. It's what drives our roadmap. Now, this is the roadmap that we have put out. We started with this several years ago and have been able to deliver on it going forward. Now, if you take a close look at it, you'll see that it includes not only hardware, but also software. So, of course, scaling up the size of the systems is one aspect. More qubits, bigger chips, modularity as well. That'll be very important here, to be able to connect different chips together with different forms of couplers. But also, you need the software, and this is what is discussed up here. We have several personas. We have kernel developers, algorithm developers, and model developers, right? And so each of these different persona will deal with different parts of, let's say, the quantum stack, right? So the kernel developers, they'll look a lot deeper at the quantum circuits, maybe also perhaps the pulses, and then all the top, you have people developing models. How do you deal with, for instance, combinatorial optimization on quantum machines? So let's dive into the middleware. What do we exactly mean by that? The middleware, for us, is the abstraction layer that enables the integration of quantum and classical resources into workloads. It's something that would allow us, let's say, to leverage different classical resources to perform certain tasks in a computation, and then also have perhaps different backends play together nicely. Now, a lot of what I will be showing today is open source. You can go and check it out on GitHub, play around with it, try it out. And in particular, I will discuss two components. The quantum serverless, which allows us to orchestrate different tasks. You can see here, for instance, on the bottom right, a small example where we would have perhaps one large quantum circuit that we want to execute. We might decompose this into sub-circuits, execute different parts on different backends like this, and then reconstruct the results. And at each step, this will require different forms of resources to work together. And then the other aspect that I want to discuss here is this circuit knitting toolbox. This is a toolbox that we are building up that allows one to take, for instance, a large quantum circuit and split it up into smaller components, and then evaluate these components on the hardware, and then tie the results back together. So if we take a look at quantum-centric supercomputing, the point in the stack that we will be focusing on today is around here, right? This particular part, the middleware for quantum. So what do we mean by this? What does it look like? You might already have heard of the primitives, which is an abstraction in some sense. If you look at the tasks that you can run on a quantum computer, you can formulate it essentially in two types of tasks. One is the estimation of an expectation value. Maybe I have some energy, I would like to estimate that energy. It's a primitive, the estimator. And the other one is the sampler. The sampler does the following. You take a quantum circuit, you execute it on the hardware, and you want to sample bit strings from this. The applications of the sampler, you can typically find them in combinatorial optimization, where the samples that you draw from your circuits could correspond to candidate solutions for your optimization problem. So the way that we think about this is the following. We have here our hardware, the QPUs and the controllers, and all of these sit behind the Qiskit primitives, right? And we will see this as the runtime as a service. And now the middleware is the abstraction layer that sits on top of the primitives here. And so going forward, when people will want to run on these systems, you will start to interface a lot more with the middleware. So let's take a little bit of a look at what we actually mean by this. What is this going to take care of? So it will take care of tasks like circuits, optimizing them. Transpilation could be something that could fit in this middleware. Transpilation is an interesting one, right? Because it has the task of taking a quantum circuit, optimizing it, tailoring it to the hardware. In some sense, it might also sit behind the primitives here. So there might be some control on what you do before or after the primitives. Now, also very important is integration with classical workflow. Let's say if I have results that need analysis afterwards and tying back together, I might want to do this on different classical resources that I have. So being able to orchestrate all of this together is what is typically going to take place here in this middleware. So with that, I want to dive into these two toolboxes and give a little bit more of an example just to make it a bit more concrete. So the quantum serverless here is designed to enable a flexible orchestration of the resources that you have for quantum and classical, and also to enable integration with other toolboxes, right, like the circuit knitting toolbox, or maybe perhaps other packages, Qiskit experiments, or so on. So let's take a look at maybe one workflow here. I want to calculate the ground state of a molecule, perhaps. And if you look at this task, it's one that you can very easily parallelize. Often what you do is you want to calculate the energy of this molecule under different configurations. Very simply put, let's say that we have lithium hydride shown here. I might want to calculate the energy of this molecule for different distances of this bond here, right? And so instead of doing all three sequentially on a quantum computer, I could do them in parallel on multiple quantum computers, right? So then here, you first need to identify a little bit these tasks, decompose them, send them to the different backends, and then reconstruct the results into let's say, some kind of nice coherent picture as shown here. So let's have a little bit of a look at some of the code that we might have. The first thing that you need to import is the Qiskit runtime service, as shown here. This will let you use, for instance, samplers and estimators. And then also the quantum serverless here, which will allow us to orchestrate different backends together into one task. Now, what we do is we start up our serverless here with the IBM cloud, and then we define here the different problems that we want to solve. So what you can see here is that I have 3 times the lithium hydride with a different bond distance. Here in red is the bond distance between the 2 atoms. And then I define the backends on which I want to run, right? So we have a fleet of backends, we have multiple ones, and maybe we can try executing on all of these in parallel, as shown here. So this is maybe what the results could look like, right? This is done on the hardware. We have our traditional variational algorithm here performing some optimization, trying to find the best set of parameters to give us the ground state, and then finally we stitch all of these results together, as you can see in this chart here. So of course there's a little bit of a discrepancy here between the ideal results and what you get back from the backend, simply because there is noise. We didn't put in much error mitigation into this example, but in principle you should be able, with error mitigation, to get this a lot lower. right? So using methods like zero noise extrapolation or probabilistic error cancellation, which is also what enabled some of these larger scale demonstrations that were put out by the team earlier on this year. So if we take another example of how this might look from the perspective of the user, what we have here is a very simple program that we might want to run. You have here a quantum circuit. It creates, it applies a Hadamard gate and then a CNOT gate. And for those a little bit familiar with the matter, this is simply going to create a Bell state, right? So entanglement between two qubits. And then we want to sample from this state. So you can see here that we are using a primitive, namely the sampler. So we will be drawing bit strings from this state. And in principle, if this is doing what it should be, you'll be drawing bit strings that are only 0, 0 or 1, 1, right? So because you have entanglement between these two qubits, you will not have 0, 1 and 1, 0. So this is the program that we want to run. And then what you can do is you can sort of execute all of this with quantum serverless, as shown here, right? So you have the program file that you're loading here. You can note that between the previous slide and this one, the name of the program changed, but nevertheless, this is the concept. And then this allows you to execute this and then get back your results. Now, Jupyter here also easily allows you to, let's say, track these. Have little widgets here where you can see the progress of the jobs. It's a little bit similar as, let's say, going onto the IQX platform to track a little bit the progress of what it is that you have been running on the hardware. And then the second toolbox that I want to talk about here is the circuit knitting. So the task of decomposing one large circuit into smaller components. And this allows us, for instance, to forge entanglement. It can allow us to decompose a quantum circuit, but it can also allow us to engineer connectivity between the qubits that might not natively be present, right? Let's suppose that you have a grid coupling map, as is often the case for superconducting qubits, and you have two qubits that are fairly far apart on the chip, right? If you need to do a gate between these two, you would need to swap all of the qubits in order to bring them into contact and perform the operation, right? But with tools like circuit knitting, you can cut a gate and then implement it virtually. And I'll show an example of this. And this can also help you implement gates between qubits that are far away, right? Now, also maybe one point to mention is that circuit knitting is a trade-off. You can engineer this connectivity, or you can split the circuit in components. The price that you are paying is that you will need to execute more quantum circuits, right? So there's a bit of a trade-off here to keep in mind. Now, let's take an example of how this might look like from the perspective of the user. A very simple circuit here. We have 3 qubits, Hadamard gate and 2 CNOT gates, and this is the input. And then another of the inputs would be the partition that we would like. In this particular case, I would like to have this circuit split in two, where I would be executing this circuit in a disjoint fashion from what is on qubit 2. And this is the partition that you can see here, right? So this would be qubit 0, qubit 1, and qubit 2, and they correspond to different partitions. And so if you analyze this quantum circuit here, you will see that there is this one gate that goes from partition A up here to partition B. And this is the gate that we would need to cut and then implement with what we call a quasi-probability decomposition. And so what happens in this toolbox is we will replace this gate here with sort of indicator gates here. And we will be replacing these local gates with the corresponding operations. I'll give a concrete example for the case of a controlled Z gate. So if I want to cut a controlled Z gate between 2 qubits, I will need to implement these 6 different quantum circuits. And then afterwards, I will stitch the results back together. So you can think a little bit, this is where classical resources will start coming into play in order to do all of this processing. Now, in this particular case, if I cut this gate, I have to execute these 6 different circuits. Sometimes I apply Z gates on the qubits, sometimes a measurement, and so on. And basically, if I carry out this process just right, I will have engineered the effect of a controlled Z gate between 2 qubits. And so this is something that allows us to split a quantum circuit into smaller components, which is a fairly useful thing to do, given that the size of devices can be limited today. Now, I encourage you to go and visit GitHub to take a look at these resources, see what the team has been doing. Everything that I showed here is open source. You can go and explore it here at these links. So I'm arriving towards the end of this presentation. I just want to remind you once again of the roadmap that we have. It's not only about developing the hardware, we also need to develop the whole software stack that sits on top of it to define the different abstraction levels, the primitives, and then see how to use them in order to get an advantage out of this particular hardware. And so with that, I'm more or less at the end, and I think this leaves us also plenty of time for questions. Thank you very much.
All right, time for questions. The first question is always the hardest, so please feel free to wonderful. Thank you.
Hello. So thanks for the talk. It was really interesting. And I'll try to make it not so hard, the first question. So so if I pull the last version of Qiskit, would I get all those things, serverless and the knitting toolbox already?
If you pull the latest version of Qiskit, if you do pip install Qiskit, you will not get these. You will need to go to Qiskit extensions to install them. But I believe you should be able to also pip install them, and it will work just like the rest of Qiskit, more or less.
So Qiskit extension is, I can access it through pip as well. With
so for instance, Qiskit extensions is a collection of repositories. One of them is Qiskit experiments. I haven't talked about this, but it's something that you can pip install. And these ones should also be pip installable.
Recently I saw a couple of things that are in your tutorials, but somehow my local version didn't have it, and probably I need to just pull those things now.
Exactly. It moves very fast. It's very active. So if you do pip install something and you have the impression that something's not there, but it should be, just go and check it out on GitHub.
All right. Thank you.
You're welcome.
Here you go.
Hi. So with the serverless example you had where you distributed the task amongst 3 different computers, so was there some kind of logic in the back end where it decides what the distribution is going to be, or is the order specified in the list, the order that it gets distributed? It's like, you can imagine if you distributed a large task to a small computer, that's a bad idea, right?
Right. So in this particular example, it's the user who defined this. Now, I think if we look a little bit forward, you would maybe want to have something that does this automatically for you, right? Let's say if you have access to a larger pool of quantum backends, you might want to distribute the tasks in a more automatic fashion based on the availability of these resources. And I think this is where a lot of interplay with, let's say, what is being doing in HPC will come, let's say, in the quantum world as well, and where we can also learn something there.
Wonderful. I think it's I don't know if there's another very short question. Else, I would thank you, Daniel, very much for your intervention and your presentation. Thank you.
Thank you.
Applause again. Wonderful.